Everyone, welcome to GEMCHEM. Now today's video is on Stereochemistry part 9 video, and here we are going to deal with conformational analysis of ethylene glycol. Now before starting, already 8 videos are uploaded in channel. You can watch it. I will give the link in the description box as well as the I button present above this video. Now let us start. So in case of ethylene glycol, we are going to deal with the third factor which is associated with conformational analysis. Now previously we have already seen that the anti-isomers tend to be preferred over the gauche isomers. This is due to that both are usually present in an appreciable extent at equilibrium, and the two factors which we have seen so far contribute to this state of affairs. Namely, we can say steric interaction as in case of butane and dipole repulsion as in case of 1,2-dichloroethane. And this case, the energy difference between anti and gauche form is larger than for N-butane, even though the steric interaction should, if anything, be smaller. The third factor which we are going to see in case of ethylene glycol is considered to play an important role, and this third factor is our hydrogen bonding. So in this video, we are going to talk about how hydrogen bonding forces the structure to stay in the more preferable gauche conformation. So in case of these two structures, anti and gauche, only in the latter, the hydroxyl groups are close enough together to give rise to an intramolecular hydrogen bond. And this fact supports that the absorption due to this bond is strong in the spectrum of ethylene glycol, which means that we can have a considerable fraction of the molecules in the gauche form, which is this one, despite the steric repulsion and the dipolar repulsion of the hydroxyl groups present here. Evidently, this repulsion is more than the outweighed by energy gained in the formation of the hydrogen bond. And we can conclude that this is not a surprising result, since hydrogen bonds may be as strong as 5 kilocalorie per mole. And when we consider the difference in the absorption frequency of unbounded and bounded hydroxyl groups, we can estimate the strength of hydrogen bond. The larger the difference, the stronger the bond. And we can say that in case of a series of glycols where the general formula is considered to be as RCH, OH, CHOH, R, here we can see that we have two forms. One is mesoform and another is DL form. In mesoform, we can see the R, that is alkyl groups, are present gauche to each other, whereas in the DL form, the R are anti to each other. When we consider R as methyl or N-amyl group, both meso and DL forms exist to a considerable extent in the conformation, in which the hydroxyl groups are gauche to each other, even though in the meso form this requires alkyl group to be gauche also. Whereas when we consider R to be as isopropyl and even more bulkier as tertiary butyl, the conformational isomer of mesoform, if we consider, there is two bulky groups present gauche to each other. As a result, the gauche conformation contributes little or nothing. And when we consider the infrared band for this, due to the bonded hydroxyl, it is very weak or sometimes absent. Now let us increase the bulkiness. This case, R becomes bulkier and the hydrogen bond becomes stronger, because when we consider this, the OH being the neighboring group for R group, the OH comes closer to each other because of the repulsion from the bulkier R group. So we can say that the hydroxyl group bend away from the bulky gauche alkyl group on the adjacent carbon, and thus they come towards each other. If we consider compounds in their gauche conformation, they appears to be more stable in the liquid state than when they are in the anti, even though hydrogen bonding plays no part. So to summarize, if we consider here, hydrogen bonding is occurring but at the cost of increase in the steric bulk. When this two comes closer to each other, the methyl also comes closer to each other. As a result, steric interaction outweighs the hydrogen bonding. In case of DL form, the steric interaction is practically nil as the R are anti to each other. This two group can come closer to each other and the methyl groups move away. Interaction of OH with methyl reduced, giving it extra stability. Some amount of energy is released by the hydrogen bonding. As a result, the structure becomes stable. Now if we shift for some more type of these compounds, that is, if we consider a general structure like this, for all the X to be as OH, OMe, NH2, Cl, Br, N, Me2, these all will undergo intramolecular hydrogen bonding. And in all these cases, active form, that is your DL form, will be more stable than mesoform. So this was the today's discussion. In the next video, we are going to deal with another interesting topic. Hope this was helpful. Thank you for watching. Do not forget to like, share, subscribe and comment.